This Zoom session is being brought to you by the Fractal Globe Snow Ring B. All right. Wow. Here we are at 8.6. End of the list of topics. So let's get on with it. The binomial theorem. Okay, this is talking about powers of sums of two terms. They're for two terms binomial. So two terms, we take powers of. Okay, 0th power is 1. First power of a plus b is 1a plus 1b. Second power, 1a squared, 2ab plus 1b squared. Now, if you work it out, the third power is 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. The fourth power is 1a to the fourth plus 4a cubed b plus 6a squared b squared plus 4a cubed b cubed plus 1b to the fourth. Okay, it's fairly obvious what the powers are doing. 4, 4, 3, 1, 2, 2, 1, 3, 1, 0, 4, and so on. It's descending order. That's fairly obvious. What's not quite as obvious are the coefficients. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. How? Well, it's simple enough. Each coefficient is a sum of the two above. That's because when you multiply this by a plus b, there's a term from here. You multiply by b. There's a term from here. You multiply by a to get an a squared b. So 1 plus 2 makes 3. 2 and 1 make 3. 0 and 1 make 1. 0 and 1 make 1. 0 and 1 make 1. 1 and 3 make 4. 3 and 3 make 6. 3 and 1 make 4. 1 and 0 make 1, and so on. So each coefficient is the sum of the two coefficients above it. Okay, that enables us to make it in general, these terms in general, you form what's called Pascal's triangle, on account of the guy who discovered it. 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 6, 4, 1, 1 and 4 make 5, 4 and 6 make 10, 6 and 4 make 10, 4 and 1 make 5, 1, and so on. So each entry equals the sum of the two entries above it. So you can extend this list down as many layers as you wish. Okay, so that's doable. It's a relatively simple procedure, although it can be time consuming. Well, so let the entry on row n, starting from row 0 here, 1, 2, 3, 4, 5, and so on, and entry r, 0, 1, 0, 1, 2, 3, 4, 5, and so on. Let's call that the binomial coefficient nr. This is one notation for it. On your calculator, it will be a big C with a subscript N and R, pronounced N choose R. Okay, so N choose 0 equals N choose N equals 1, because we have a 1 here, 1 right here, and 1 all the way around here. N choose 1, N choose N minus 1 is N. 0, 1, 2, 3, 4, 5, etc. 0, 1, 2, 3, 4, 5, and so on. We will define and choose n, yes, and choose n. 1, 1, 1, 1, 1, 1, 1. Okay, easy enough. Now, I found n choose n because this is connected to something called combinatorics, where there's a number of ways to choose an R element subset from an n element set, if ordinary doesn't count. Well, there's another definition, a personal note. In elementary, no, not elementary, junior high school, I rediscovered Pascal's triangle, but I never was able to figure out the closed formula for it. Pascal and his friends did, so they get the advantage. So, okay, is a closed form formula. It involves something called the factorial, written n exclamation mark. Call that because how quickly it grows. We define 0 factorial as 1, and for any integer bigger than 0, we define it as the product of the numbers from 1 up to n. So 1 times 2 times 3 times 4 all the way up to n. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 1 times 2, which is 6, times 3, which is 6. 4 factorial is 1 times 2 times 3, which is 24. 5 factorial is 120, 6 factorial is 720, etc. Basically, to get 2 factorial, you take 1 factorial and times 2. To get 3 factorial, you take 2 factorial times 3 makes 6. 6 times 4 makes 24. 24 times 5 makes 120. 120 times 6 makes 720, and so on down the line. 10 factorial is 3.6288 million, big number. It turns out factorial is a number of ways to order n things in a row. So there's 2 ways to order 2 things in a row, 6 ways to order 3 things in a row, and so on. So about 3.6 million ways to order 10 things in a row. it grows very quickly there for the exclamation mark. Now, all right, I won't prove now, but or in this course, but when you get to statistics and probability, they'll talk about binomial coefficients defined from factorials. N choose R is n factorial over r factorial times n minus r factorial. That's a formula, and then they usually figure out what n choose R is without going through all the previous rows. Although these are sometimes rather annoyingly large numbers, and some of these terms in the Pascal's triangle, especially when you get further down, get kind of big too. All right, now there's I'll go about going through the irritating part of proving it by mathematical induction, which is what we covered last time. The idea is that if we can prove this for some initial case, and then prove that if it's true for a certain case, it'll true for the next case, that it proves for all. So it's the initial case for the edge of Pascal's triangle. N choose 0 equals n choose n equals 1. So let's prove that these ones go down here and here. Well, let's see. Well, it's easy enough. We take n factorial over 0 factorial times n minus 0 factorial. It's n factorial over 1 times n factorial is 1. And if we put an r equal to n in here, then we get n factorial over n factorial, n minus n factorial. Here's a 0 factorial, again 1, and again you get 1. So that confirms the initial step. The formula with the factorials works for combinatorics and choose R along this edge here. Now for the inside. Well, for the inside, we'll use, we will assume that the formula works for k minus 1. So that k choose R equals k minus 1 choose R minus 1 plus k minus 1 choose R. It's true for all R for k minus 1. Now let's prove it true for the next value, for n equals k. So let's find k choose R. What is that? Well, so sum of the two above it. That's how the Pascal's triangle worked. Each entry is the sum of the two above it. So it will be k minus 1 choose R minus 1 plus k minus 1 choose R. Now, assuming the formula works for k minus 1 here and k minus 1 here, this will be k minus 1 factorial over r minus 1 factorial times k minus 1 minus r minus 1 factorial. This will be k minus 1 factorial over r factorial times k minus 1 minus r all factorial. And okay, we simplify it a bit, and we do a little bit of algebra. Use that a factorial is a times a minus 1 factorial, so that this will write as this and this as this. And a little bit of work later, we get that it's true for that. Basic algebra, we'll let that be. So if it's true, it's this formula is true on the edges of Pascal's formula, and it's true all the way down Pascal's triangle. So it's generally true. So we can use this as a general formula for Pascal's triangle, and which brings us back to powers of binomials. So it follows the binomial theorem. The nth power of a sum, a plus b to the nth power, is n choose 0 times a to the n plus n choose 1 times a to the n minus 1 b to the 1 plus n choose 2 a to the n minus 2 b to the second, and so on, all the way up to n choose n b to the n, with the kth term being n choose k times a to the n minus k b to the k. So for example, 6 power of x plus y. We have 6, 5, 4, 3, 2, 1, 0 for x. 6, 2, 0, 6, 2 is 1, 6, 2 is 2, 6, 2 is 3, and so on. We'll make up the Pascal's triangle. Fifth row is 1, 5, 10, 10, 5, 1. 1 and 5 make 6, 5 and 10 make 15, 10 and 10 make 20, 10 and 5 make 15, 5 and 1 make 6, 1, 6, 15, 20, 15, 6 and 1. So 1x to the 6th plus 6x to the 5th plus 15x 4 y squared plus 20x cubed y cubed plus 15x squared y to the 4th plus 6x y to the 5th plus 1 y to the 6th. Okay, and so let's go with some problems. What are these powers of, what are these combinatorics? 3 choose 1 times 4 choose 2, what are they? Well, rather than going through the formula, which is annoying, 3 choose 1, that's 3 factorial over 1 factorial times 2 factorial. 4 choose 2 is 4 factorial over 2 factorial times 2 factorial, which after a little bit of working out makes this is 3, this is 4 times 3 over 2 times 1, which will be a 6. 3 times 6 is 18, and there we are. Here we have the sum of 5 choose k for k going up to 1 to 5. What is it? Now, if you look at this and look powers of 1 here next to them, you get basically, if you put 1 here and here, all these powers of a and b are just 1, and you just get a sum of combinatorics. And so this would basically be 1 plus 1 to the 5th power, which is 2 to the 5th, 32. Here we have an alternating sum of combinatorics. 5 choose 0 minus 5 choose 1 plus 5 choose 2 minus 5 choose 3, yada, yada, yada. Here, it works if we set that x be 1 and or a be 1 and b be negative 1, so as to make this alternation. And so this becomes a 5th power of 1 minus 1, 0 to the 5th is 0. These completely cancel out. Again, that should make sense because 5 choose 0 and 5 choose 5 are equal. These turn out to be equal and these turn out to be equal. In fact, in general, Pascal's triangle is symmetric left for right, so you should expect an alternating sum to cancel out. Okay, that concludes that part. Basically, we're done for this. The book problems consist of basic arithmetic questions like that. So all you really need is this formula, and remember what the factorial is, and this formula to see how it uses for the binomial. Okay, that concludes our talk here today.